Hi everyone, I'm Chris Saxon, and today we're going to be looking at how we can write scalable SQL using Oracle Autonomous Database. So if you've been writing SQL for a while, it's almost certain that at some point you've been asked to tune a slow running query. And when you need to do this, there's various things you can look at or do to make it faster. First thing is, are the underlying stats for the tables it uses correct and up to date? This is the information the optimizer uses to decide which tables to access or how to access the tables and which order to join them and so on. If this information is missing or wildly inaccurate, it's the garbage in, garbage out principle. The optimizer is unlikely to find a good plan or the best plan available for your query. Good thing is, in Oracle Database, for a very long time now, we've had the default stats gathering job. So for the most part, you don't really need to worry about that. So, assuming the row estimates and the stats are good and reasonably accurate, the next question to ask is, can we access the data faster? One of the most common ways to do this is by creating an index. And with the advent of automatic indexing in 19C, the database can do this for you. It can analyze your workload, look at those statements, and ask, will creating an index make this faster? If the answer is yes, it can go ahead and do it for you. And this is great because it kind of saves you from that firefighting performance tuning that sometimes you probably experience, where you get call out at the weekend or 3 in the morning or some other inconvenient time. And it turns out that all you needed to do was create an index. Because this is always running in the background, if this happens, it can create the index and you'll never need to be woken up and worried about it. And increasingly, Autonomous Database is able to do other types of physical tuning for the statements. Things like automatically create materialized views, load the tables into the in-memory column store, automatically partition the tables, and so on and so forth. There's a whole bunch of physical tuning options that we've got in the database that we can apply to the SQL statements. We know what the workload is, we know what the queries are, we know what the toys and tricks in the database are. Stands to reason we could create a program which just analyzes those and figures out which are the best to create to improve your query performance. So this is great. And like I say, this can help you avoid a lot of performance firefighting. But there's one thing that it doesn't matter how good Oracle Autonomous Database gets, there's one thing it will never be able to do, and that is know, is this the right SQL statement to run? Should we change the query? Should we rewrite it? Or should we throw it away and rewrite the entire process? It just doesn't have the business context to make those kinds of decisions. And it's I won't say never, but it's not going to be able to do that for a very, very long time. So that's what I want to look at today. I'm going to look at 3 things that it doesn't matter how good Oracle Autonomous Database gets, how much its automatic tuning gets, it's still likely to have slow SQL performance. To do that, let's imagine we're building a simple retail application. We've got a product catalog, and start off with, we're going to build the product details page. So we need to write a query to fetch the details for a particular product. Pretty straightforward, probably selecting from the products table by the product ID. And we might write a query that looks a bit like this, selecting blah, 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 and concatenating in the product ID that we're searching for. So this is the first problem I want to be talking about, using string concatenation to construct SQL statements. Very, very specifically, concatenating user input into the queries in your database. We'll see exactly why this is a big, big problem in a minute. But first, I want to explain what happens when you send a SQL statement, when you send a query to the database, how it actually processes it. So SQL is not a compiled language. Each new query you send, the database has to go through a process known as parsing. The first step in this parsing chain is what's called the syntax check. What we are passing actually, does it conform to the rules of the SQL language? If I send sleeked form here or some other gobbledygook nonsense, that's not valid SQL, right? So that's going to fail the syntax check. Let's imagine I've written something a bit more legible, select star from some table or the other. We move on to the semantic check. So we've got something that meets the rules of the language. We now need to ask, are we actually accessing real tables and columns? And do we have query privileges on them? So if I'm querying a non-existent table, Even though it's a valid statement, that table doesn't exist, so it will fail the semantic check. Assuming both of those have passed, this is where the optimizer comes in. It needs to consider various ways of accessing the data, index, full table scan, how to join the tables, and so on and so forth. So it considers the possible plans, ranks them, and chooses the one that it thinks will be the fastest. For example, maybe we're going to do a full table scan. Having chosen a plan, it then needs to turn that into something a computer can actually execute, your database server can run. So this is the row sourcing phase. A full table scan means read this sectors of this file on that disk, and so on and so forth. And then at last, after going through all that work, we can finally execute the SQL statement and get the data if it's a query. So this is the process of parsing. So what's this got to do with everything? Well, let's go back to the query we had before. We were using string concatenation to search for different product IDs. What this means is for each new product we're searching for, we get a new SQL statement. And the database has to go through that full parsing stack for each one of these. But if we think about these are basically the same, right? They are syntactically identical. All that's changing is the number we're searching for. Semantically identical, we're accessing the same tables and columns. And at least in this case, let's imagine it's nice and simple. We're just selecting from the products table by primary key. We would expect an identical plan. It's not always the case, but it is often the case. So if we go back to our parsing stack, because they are the text of each of these statements is different, the database has to go through this full parsing stack for each new product ID we search for. That's not great, right? And these optimization and row sourcing phases are particularly CPU intensive. You spend a lot of time actually figuring out how to run the statement. It's kind of meta work. It's like planning, figuring out what you're going to do. It's not actually doing the real work. So the less time we can spend doing this, the better. So we want to avoid this as much as possible. So having to go through this full parsing stack means the database is doing extra work. But there is actually a much bigger problem lurking when using string concatenation. If we do this, we are trusting that the users are actually going to pass in valid product IDs. That may not be the case. As soon as you take user input and make it part of your SQL statement, you're at risk of SQL injection. So what does that mean? Well, instead of just passing in a product ID, they might also add in the lovely all 1 = 1 clause. How does that affect things? Well, 1 = 1 is true. Anything or true is true. So what this means is we can then see every single row in the table. Oh, that doesn't sound great, right? So already we're on shaky ground. But you might go, well, it's our product catalog. We want the customer to see it. It's not too big a deal, right? Well, not only can we see every row in the table, we can chain queries together with union all. This allows us to access every table we've got query privileges on, potentially things like payment information, customer details, so on and so forth. That is stuff that you definitely don't want anyone to see. So if you're using string concatenation, taking user input, making it part of your SQL statement, it's only a matter of time before you're hacked and your front page news because there's been some kind of data breach. So this is so bad. How do we stop it? How do we avoid getting into this problem? Well, fortunately, the solution's super easy. Just use bind variables. Instead of concatenating values in, our SQL statement is select star from whatever table where the ID equals a question mark, or it might be colon variable name, depending on the language you're using. The key thing here is the text of the SQL statement stays the same whatever product ID we search for. This question mark is a value placeholder which we bind in at runtime. What this means is that user inputs never become part of the SQL statement, and therefore SQL injection is impossible, right? So it doesn't matter what they pass in. The best case, the SQL statement will just return no rows. So this is absolutely critical to keep your data safe. But there's also a nice performance advantage this has in Oracle database. If we go back to our parsing stack here, after the semantic check, the database says, have I seen this statement before and already come up with an execution plan for it? Is it in the shared pool? If the answer to that is yes, then you can go, well, rather than trying to figure out a new way to run it, I'll just reuse the plan I've got, bypass those row sourcing and optimization phases, and just go straight to running the query. So this is what is called a soft pass, when we bypass the plan generation steps. And this can be a considerable time saver. So if this is so, if using bind variables are so important, they keep our data safe and can make our queries faster, why don't we just always do this all the time? Well, let's look at an example of how we'd actually bind it in. We've got to prepare the statement, bind the values, and then actually execute it. I mean, it's not a huge deal, but it is more code than just like statement.execute with concatenating the values in. And if you don't know the security and performance differences here, I certainly didn't when I started as a developer, then you just go, well, I'll stick with the easy, obvious approach, right? Why write all this extra code if I don't need to? So key thing here is be aware you absolutely need to do this. And this is the case for pretty much all programming languages. The safe, secure, fast way to write SQL is more code than the unsafe, slow way to write code. However, there is at least one language that flips this on its head, and that is PL SQL. The easy, obvious way to write statements in PL SQL, so static SQL, binds by default. So if you've got any variables or parameters that you use in your query, they are bind variables. You don't have to do anything special for you. The database will handle that. You can write an unsafe SQL in PL SQL, but you kind of have to go out of your way to do it. So there's good reason to think and consider, how can we keep our data safe? Key thing here is make sure you use bind variables to keep your data safe and improve query performance. So let's move on. Hopefully we're building our retail application. Hopefully customers have found things they want to buy, they've put them in their basket, they've gone through their journey, and they come to the point where it actually comes to buying. So they enter their payment and shipment details and so on, and hit the big button, and then they have to sit and get one of the lovely waiting screens and sit there for a little while. It takes a while to actually save the data to the database. And it's like, well, why is this? Well, there's several possible reasons, but let's imagine one scenario. So hopefully, let's imagine customers, they're buying lots of stuff from us. So we've got lots of different products. And what we're doing is we're going to iterate through the products that they purchased. And for each time we loop through those, we're going to send a new statement to the database. We're going to insert that product into the order items or order details table. And overall, this process can take a long time. So if you're an app developer, you're like, database is slow, it's taking a long time. But if you're a backend database developer or DBA, all you see is a bunch of single row inserts. They're super fast, and there's very little you can do to make them any faster. You're like, the database is fast, there's nothing I can do here. So it can lead to this classic battle, which you probably experienced one way or another, where the app developers are going like, the database is really slow, make it faster. And the DBAs and backend developers are kind of going, well, it's quick, it's your problem, right? So it's like, why is there this disconnect? What's going on here? Well, the problem is, like I say, we're running these SQL statements in a loop. That means there is a lot of back and forth from the application to the database. In particular, what that means is we are spending a lot of time on the network. That is the real culprit here. So network is usually the slowest component in your architecture, usually by an order of magnitude or more. So the more back and forth we do, the more time we're wasting just sending data around rather than actually processing it. So this is the next problem I want to talk about, and the thing we want to avoid, and that is putting SQL inside loops. So how can we address this? How can we stop doing this? Well, we've got data coming from a client, particularly if it's got an array of things that we want to process. The best way to do it, to avoid this, is to use bulk processing. So how do we do that? Well, here we're still going to iterate. We're still going to loop through all the products that the customer is hopefully purchasing. But instead of on each iteration sending that insert to the database, we are going to build up a batch. We're going to collect them all together into one group. And then finally, once we've consolidated them all, send them all in one call to the database. So this can then significantly reduce the amount of round trips we do from the application to the database and back again. So this on its own should give good performance advantages. But if you think something like creating an order, we'll typically have to write to several tables. Certainly the order header and the order items table, so at least two, but possibly or probably payment tables, invoice tables, shipment tables, maybe the customer table, and so on and so forth. So we could still have quite a few round trips here. Rather than one per row, we could have one per table. So how can we reduce this? How can we shrink this down even further? Well, we can go back to using PL/SQL again. Here, we put everything in a PL/SQL block or a stored procedure, and in one call to the database, we process all the data. So here we're inserting into the order header and then adding the order items. A couple of little interesting details I wanted to call out here. First up, this returning clause. It's a good chance you've got some form of auto-generated primary key values for your tables. When we're doing that, we can use the returning clause to fetch those, so we don't need to re-query the table or pre-generate them ahead of time. We can just get that generated primary key value from the insert that just executed that. We can then use that to insert into the order details, the corresponding master detail relationship. And we've got here a for all statement. Now, although it has the word for, this is not a for loop. This is bulk processing in PL/SQL. So the SQL and PL/SQL languages have different runtime engines. And with a for all statement, we consolidate together all the things, the whole array of inserts, and send them in one call to the SQL engine. By doing this, using PL/SQL, instead of having all that backwards and forwards from the database, we pass everything in one call, process it all, and then return control back to the client. We've eliminated the network as much as absolutely possible. So hopefully giving us some good performance gains in the process. So at this point, customers purchase their goods. We need to start off some back-end processes to actually send it to them, right? So for example, we need to start the process of shipping the goods. And the code, you might write something like this to do that. Let's imagine you're writing a batch process to find the unshipped orders and start the process of actually sending them where they need to go. So this looks fairly clean, fairly straightforward. You might go, what's the problem here? Well, if we think about this get unshipped orders method, somewhere buried underneath it, there's probably a query a bit like this. Find everything where the shipment date is null or the status is unshipped or whatever. Having fetched all that data from the database, we then need to iterate through those and insert and update those, insert them in to the shipment record and mark the order to say that it is now shipped. So we're back to a situation of having SQL inside a loop. And again, we're coming from the application here, so we've got a lot of network in the process. So we could stick the whole thing into PL/SQL again. We could have our loop, loop through them and do our insert and our update. This eliminates the network, but we've still got a loop here. We've still got a loop that we're inserting or updating rows one at a time inside it. If you want to write slow, like really slow database code, the absolute best way to do it is to have a loop, put a SQL statement inside it that processes the rows one at a time. So even though we've eliminated the network, this could still potentially be quite slow. It could take a long time to run. So how do we avoid this? How do we stop this? How do we make it faster? Well, the key to fast SQL is to have one statement that processes all the data. So you want to process it all in one execution. So how can we do that? Well, here we need to load the unshipped orders into in the shipment table and then mark them complete. So we can do that with an insert, a select, and then a single update to set them. Sounds great, right? There is a potential problem lurking here. What happens if two people try and execute this at exactly the same time? Let's say I start running this. I load in some unshipped orders into the shipments table. Immediately afterwards, you start as well. So before I've completed, you will then start loading the same unshipped orders because I have not marked them as shipped yet. We're potentially sending customers 2 lots of each of the goods they've ordered. All right, make your customers nice and happy, but the finance and so on team's probably pretty upset about this. So how can we avoid this? Well, one method is to flip them around. Do the update first and then do the insert. How does that help? Well, only one user at a time can run an update. So if I start this update, I lock those rows, you need to wait for me to commit or roll back to before you can go ahead and then run the process too. So we solved the concurrency problem. But we've introduced a much, much bigger problem, right? We've just marked everything as shipped, and then we're going to try and insert the unshipped stuff. There's nothing there, right? There's nothing to load. So we've gone from double shipping stuff to sending customers nothing. Okay. So how can we get around this? Well, one way, that returning clause. Not only can we use it on single row inserts, we can use it with bulk collect and get the details of all the rows we've just updated. So we can get all the orders we've just set to shipped and these for all processing to load them into the shipments table. Because we've got an array, we know what they are and we can actually process them correctly. So now hopefully the customers will get everything they want. And at this point, the business probably wants to understand how sales are going, how things are actually performing, run some analytics. Really common type of query is to get the running total of orders over time. So in order to do that, we're going to query the orders table. We get the running count of how many. So we're going to have a count function, and then we can have a scalar subquery to find everything ordered before the current row in the data, right? Well, there's a problem here. The problem here is we're accessing the orders table twice. So at least we're doing at least double the work we need to. But in the worst case, it could get a whole much worse than this. Worst case, we could execute this scalar subquery once for every row. If there's 1 million rows in the orders table, we could run that subquery 1 million times. That sounds pretty horrendous, right? So this is something we want to avoid. We want to avoid querying the same table many times in one statement. Now, I will say this one's a bit more of a guideline. The first two are things you want to avoid at all costs. There are legitimate reasons, but it is a sign that maybe you should change things. So how can we solve it here? Well, the solution in this case is analytic functions. Instead of counting in a subquery, what we'll do is have the count function, but add the over clause. Unlike regular count, this preserves all the rows, and then sorting by order date gives us the running total sorted by date. So we've got our orders table, and we're on this row on the 1st of February here, and this is the 100,000th row in the table, so it's row 100,000. We'll get the running total of 100,000, running count, right? Maybe, right? Maybe. Why maybe? Well, what happens if there is a row the next row has exactly the same date as the current row? Well, if that is the case, that row after you will get included in the total. So even though we're on row 100,000, the running total for the current row will be 100,001, and it will be for the next row as well. What this means is you can have several consecutive rows with a running total that is exactly the same. Not what most people are thinking of or looking for. When they want the running total, they probably expect it to increase for every single row, right? So what's going on here? Why does this happen? And what can we do about it? Well, when we have an order by clause in analytic functions, the default window is range between unbounded preceding and current row. Include all rows with a value less than or equal to yourself. If rows after you in the results have the same value, they get included in that total, and we get the running total, which stays static for several rows. Like I say, it's useful in some cases, but most of the time not what people are looking for. To ensure it increases for every single row, each new row in the dataset, we change range to rows. So this means only include the previous rows in the dataset. We're on row 100,000, the running total will be 100,000. Job done, right? And now we get what we're looking for. Each new row, the values actually increase every single time. So, covered quite a bit of stuff here. We've looked at various ways we can make our queries faster. Key thing with this final one is we want to eliminate the table appearing many times in a query. And at this point, some of you might be a little bit skeptical and kind of be like, does it really make that much difference? Can it help that much? Well, I've got some examples here. So let's just create an empty orders table. And what I'll do is I'll just query it 5,000 times. So I'm doing it using string concatenation and again with using bind variables, right? So we're just doing 5,000 row lookups. The table's empty. I've just created it. So we're pretty much just measuring parsing costs here. So let's just have a look and see what's going on here. So using string concatenation with all that parsing work, just over 7 seconds. Using bind variables, under 1/10 of a second. A mere 118 times faster, right? This is significant, okay? Okay, you're not going to notice it on each individual execution, but scale that up across, a busy system. This can really slow things down. So parsing costs are real. But as I said, the biggest problem we have here with string concatenation is SQL injection. You absolutely want to avoid that. Make sure you use bind variables, folks. Right, next, let's insert 100,000 rows in the table, and we'll do it using a for loop, and we'll do it using bulk processing in PL SQL, so a for all. So this will insert the rows one at a time, and this does bulk processing. And as we can see, using the loop, inserting rows one at a time, around 2.5 seconds. Whereas we're under half a second if we use the bulk processing. So about 8 times faster. So again, putting SQL inside a loop is the best way to make your SQL slow. To avoid it, we'll use bulk processing. We can use bulk processing. So that's creating the orders. Let's get on to the shipment process. So we've got our whole bunch of orders, and they're all new because we just loaded them into the database. We've got 100,000 of them. And what we're going to do is iterate through them. So this one will take a little bit longer than the others. But as you can see here, I've got a for loop, and then one at a time inside it, we're going to insert one row, update one row. Absolute best way to have slow SQL this. We want to avoid this. What we want to do instead is have our update, which processes all the data. So this will update all 100,000 rows, and then we're going to use bulk processing. Cursor's flying off there. We use bulk processing to insert the shipment information. So what's the difference here? So nearly 8.5 seconds doing the SQL inside a loop, and around 3.5 seconds when we got a single statement update and our bulk processing. So nearly 2.5 times faster. Not quite as big as some of the other gains, but still pretty significant, right? That's time we don't have to spend running CPU. Okay. Finally, let's look at our analytics. Okay. So this time we've got 100,000 rows in the table. I'm just going to do it for 50,000 of them, just so we're not here all day. So we've got it using our scalar subquery, and then we've got it using our overclause, our analytics. Notice I'm using our window clause. It's a new 21C feature, which allows us to refactor it and define it in one place. So that's completed. Let's just see the difference here. So about 13.5 seconds using our scalar subquery, 1/10 of a second using analytic functions, 135 times faster. This, that's huge, right? Why such a performance difference? Well, let's have a quick look at the plans. We can see using, helps if I get the right one, using our scalar subquery. No, I've got these. There we go. That's the one I was looking for. So using our scalar subquery, we can see it executes that 5,000 times and processes 127 million rows. Okay, there's only 100,000 rows in the table. That is a lot of wasted effort. No wonder it took so long. Whereas if we saw with our overclause, we're only processing the 50,000 rows we actually queried. So that is why it is so much better. All right, to finish up and recap, as we've seen, Oracle Autonomous Database has lots of toys and tricks which can run automatically to improve your query performance. But there are things you want to do or avoid to ensure fast SQL. String concatenation of user input. Absolutely make sure you use bind variables to keep your data safe and avoid parsing costs. SQL inside loops. Again, you want one statement that processes all the data or use bulk processing. Finally, having the same table appear many times in a query. It's a sign that maybe there's a better way to write your query. So all that's left for me to say is I really hope you enjoyed this. More importantly, I hope you learned something. I'm Chris Saxon, and I hope to see you again soon. Goodbye.